there, right? So, but specific USB or SPI, any specific these things, right? So apart from the examples that we are considering, so we will take it offline for other programs, online series programs, or even support what you need, because what we are observing is some of the faculty members and they whoever doing research work, they need support, but as part of this internship we cannot provide much support here, because those are kind of advanced work, right? See, without explaining SPI protocol, I2C protocol, USB protocol, if I just do the synthesis of it and then you get all the gates, it doesn't matter for you what it is, what protocol it is, right? But I first, in the front end, I'll have to explain and then further taking it, right? Anyway, now synthesis people need not have to know the protocol. Physical design people need not have to know the protocol. They need to know other aspect, like what is the frequency USB 2.0 supports, so USB 3.0 supports, right? And those kind of optimization related. So that way, please pardon us, on these specific aspects. So we can support outside this program. This is an internship program. So this is what is aligned with NTUPL as well. Because
Okay, like for today's physical synthesis session, we have took the module of I2C itself with an interface of some FIFO blocks and all. So I think you can relate when you execute the same thing on your code.
yeah. So only thing is I2C design per se. Okay, how I2C works, right? Those kind of things, Shravanti, you are also not covering, right?
Yes, yes.
Writing on it. Okay. So, but not that we don't know, we can do that. It is just the limitation of time and also the scope what we have set for the synthesis sessions. Hope that clarifies. Okay, go ahead.
Okay. Have completed till the introduction of physical synthesis. We just gave a brief idea of what are the inputs that are needed for the physical synthesis process. So these are the list of the inputs and the outputs we generate usually while doing the process of physical synthesis. It's the same process of how we are performing the logical synthesis, but the extra input we give are the physical libraries and a physical information file called as a def or a design exchange format file that we'll be resourcing it from the Innovus tool of the physical design implementation, so that to optimize our gate level netlist in the terms of power, area, and performance. So likewise, before for the logical synthesis also, we took these inputs. Those are nothing but my RTL code, libraries, and the constraints file. Now these two are the extra inputs that we are getting introduced to you guys today. So let us know them in a descriptive way. What is the left file and the def file? Now, till now, there was only a logical library file where you will see the functionality and timing information of each and every gate. I mean to say, there you'll be having some transition times and the load times, and for the respective transition and the load values, you will see some delay values for each and every cell. There, in that particular library file, the functionality will be defined. But when you need to implement those cells physically, you need some metal information or some physical information regarding that particular cells or the gates. So that information we can't get it from the library file. There is some other file that is called as physical library or the .lef file. Lef is nothing but library exchange format file, where you can get to know the physical information of that particular gate that you have used in the library. So what is physical library is a abstract view of the gate level netlist. I mean to say, whatever gates are there in the library, the abstract view of that particular cell information will be there in the physical library file. Now, what does the physical library contains is, it will give only an idea about the PR boundary, that is nothing but the placement and routing boundary of that particular cell. So what will be the size of that cell and what is the interconnect that particular cell can handle, that range of boundaries for that particular gate will be defined in this library. And the pin position, so for whatever gate level netlist you have port objects in your gate level netlist. But what about the internal pin objects? If you just take an example of a gate, so there is an AND gate. So there are three pins, two input pins and one output pin. So let us take this as A, B, and the output is Y. Now, what is the pin size of this particular A pin and what is the pin size of this particular B pin and Y pin respectively, when it has to occupy physically, when it has to get implemented physically, what is the size that pin of that particular cell have to contribute when it is going in a physical format. So that and all attributes means to be the pin position and the metal layer information of that particular cell. So the metals, whatever interconnects, so for a pin it can't directly connect without any I mean to say without any metal information. So there needs to be some interconnects for that particular pin, with what metals that pins can connect to the other gates or to some other logic. So that and all information will also be there in the left file itself. So physical library formats are in .lef. As I told you, lef is nothing but library exchange format. So it contains the physical information of the standard cells, macros, and pads, IO cells necessary for placement and routing. Placement and routing is nothing but when you go to the physical design stage, there is a stage called placement and routing where you bother about the connections of the logic. So you usually use this physical information file in that stage. Now, what is a macro here is, cells are nothing but your logical gates. Those are the gates which are there in your library. A macro is nothing but a memory element or some predefined logic. So macros are some memory elements. Example, for any design you need some memories like RAMs and ROMs. So that memory implications will be coming in a physical format as a macro. Now what are pads is, now, when you consider a top level module, I mean to say when you consider a full chip, there will be some input and output ports for your top level RTL code. So to connect this pins to the outer world, I mean to say that to communicate these pins with the outer world or the environment, you need to have some extension for this ports of your top module. That extensions are called as pads. So pads are nothing but the extension metals. Those are assigned for your input and output ports of your netlist. So these are basically used when you need the communication when they get implemented physically and to communicate with the outer worlds. So it also defines placement unit tile. Unit tile is nothing but the height of the cell. It is another term for the height of the standard cell or a gate, and the height of the placement rows, preferred routing directions, and the pitch of routing. So what are these attributes? I'll be telling in the later slides. Now, abstract view, that means the physical view of a cell, also contains this following information, that is the cell name, the name of the cell, that is same as the cell name in the library file, and the size of the cell, that means how much area it is going to occupy when it is getting physically implemented, and allowable orientation, that means the cell have to be designed in a clockwise direction or an anti-clockwise direction. And the pin names, as I told you an example of AND gate, what are the pin names of that particular gate, layout geometries, so routing blockages, and power and ground pins, and process antenna area. So these terms you will be getting to know slowly from the later slides. So these are the information for each and every cell you have in a library exchange format file. So left abstracts lower level geometrical details of cell. So what a particular cell is, how much in a particular cell, how much area it has to contribute for a power rail, how much area it has to contribute for the input pins, and how much area it has to contribute for the output pins. So that lower level abstraction of each and every cell will be detailedly mentioned in a left file. So it provides all the details that are required for the router to connect to the cell without impacting any internal cell constraints. So what does that mean is, it will not bother about the functionality, because the functionality is already mentioned in the library file, so it will not affect any internal cell constraints or whatever functionality is defined for that particular cell. It only bothers about the attributes, the physical attributes specified for that cell. So as I told you, a cell specifically looks like this. If you just take an example of this NAND gate, so for a NAND gate there are two inputs, one is A and other is B. So whatever drawn abstract view is there, you can see the metal, how they are using for that particular pin. So it is surrounded by a metal with a blue color implication. So that is nothing but the physical attribute of that particular pin when you may want it to interconnect when you're doing physical design flow. So these are some blockages you can see, as I mentioned in the previous slide. For each cell, you will be having a height information. So this is your cell height or the unit tile information. And this is the metal aspect defined for the VDD and VSS, that is nothing but my ground. So this area is occupied, or this metal is usually used to connect the power rails. And these are the A and B pins that are input pins, and this is my output pin. And symmetry is XY or 90 degrees. So it is 90 degrees straight. It is just clockwise, not anti-clockwise, and some blockage of that particular cell. So blockage is nothing but in that particular area, nothing, no pin should be coming or no interconnect should be coming according to the defined blockage area inside the cell. So blockage is nothing should pass on that particular area when it is physically getting implemented. So if you see when in a left file, the attributes will be defined something like this. So let us take an example. This is the layout of the cell. Okay, this is an example of a simple inverter. And this is the abstract view. That means only the pin information, lower level abstraction when it comes to the pin information of that particular cells will be there. So you can see a macro IV will be defined according to the name. IV is nothing but inverter. The library name given by the foundry for the inverter is IV, and the class is core. So the foreign exchange, that is the origin of that particular cell. That means your origin of the cell will be starting from lower left. So the origin of the cell is defined as 0, comma 0, the xy coordinates of that particular cell. And the size is 3 by 12. That means 3 will be my width of that particular cell. 3 will be the width of my particular cell, and 12 will be the height of my cell. So 3 by 12 totally comprises of the total area occupied by that cells. So it is width by height, and symmetry is xy. That means it is oriented in the xy axis. That is straight 90 degrees, and the site is core. So I'll come to that. What is core? What is block section? Now the internal terminals. So for the pin, the direction is input, and the antenna size, when you these are all the attributes that you get from the foundry, so that you don't face any physical issues, physical parameterized issues, when you take it to the DFM stage or later stages. And what metal it has to use for that A pin is metal 1. So there will be some layer of metals like metal 1 to metal 9. So for this particular pin of that particular cell, it has to use the metal 1. Usually the lower metals are preferred. Now for that pin, what is the box area? So if I take this is my A pin, what are the box coordinates of that? So 4 box coordinates of that particular block will be defined in a rectangular form for that particular pin as this coordinates. So for each and every pin, they will be defined. So I didn't mention everything. So I just took an example of one pin and what are the attributes that will be defined for that particular pin. So later on, all the pins of that particular cell will also be defined in the same way. Now, next is the obstruction. So in the previous slides, as I mentioned, there will be some blockages for a particular cells. So a metal layer should not pass on that particular coordinates of this complete cell. So for this cell, they have defined some obstruction. OBS is nothing but obstruction. So there will be some obstructions given by the foundry itself, because those if the metal is passing on that obstruction, there will be some issues when they are going to take it to the manufacturing. So they define obstruction or blockages for each and every cell using the coordinates again. So among this cell, these are the coordinates where my metal should not pass or metal should not overlap in this particular box coordinates. So OBS is the obstruction or blockage for that particular cell. Now, let us come to the class. There are three types of classes when you take a left file. One is core, one is block, and the other is routing. So class core means you are seeing a left file of a gate. If it is a gate or a simple standard cell or a logic gate, the class will be core. Now, when a class is a block, so there will be some other classes, left files also. It's called as block. We'll see in the demo session. So if the class is block, that means the left file is related to some memory object. So there is another class also called as routing. So that particular routing class is used for the interconnects. So not internal of the cells. When you define another left file, that will come. So remember this, class core is for the simple logic gates, and class block is for the memory elements, and class routing is for the interconnect information. Now, this technology, there is till here is, are there any queries? This completes my standard cell left description. So are there any queries regarding this standard cell left file? Shall we move on then? Okay. So
Yes, you can.
yeah. So I'll just repeat once what is this OBS. OBS is nothing but obstruction. For that particular cell at this coordinates, metal 1 should not pass. That is mentioned in the left file of that particular cell. So for this particular cell, an blockage for the metal 1 is given at this coordinates. There is an other technology left file. So now for the internal attributes or internal physical parameters of the cell, there is a file defined. Now what about the interconnect information? That means if this cell has to connect to some other gate. Now I have an A pin. Now this inverter A pin have to get connected to some AND gate. I need some wire. So what about this wire metal properties? Right, so I need to have some file where I have the attributes that have to be defined for the metal interconnects also. Those are nothing but wires. So that particular file where the wire metal properties or wire physical properties are mentioned are called as technology left. So this file is also again given by the foundry itself. In the synopsis tools or you will have an other file with an extension called .tf, and in the cadence you will have a format called as .tech.left. Dot .lef is a cadence file format, as I told you. .tf is a synopsis file format. Now, cell height is measured usually in the tracks. Okay, so if you take an example of the previous cell, uh, take an example of this particular inverter gate. This particular cell will be divided according to the tracks. So each cell will be having a number of tracks that it has to occupy when it is going to the physical design implementation. So that's the reason in the technology file, the track information of that particular cell also will be mentioned. So a track is the one metal pitch, and an 8-track cell has a room of 8 horizontal metal vials. That means it can surpass or it can pass on it 8 metal tracks when you consider a cell of 8 tracks. So a track is a one metal pitch. So what is pitch? I'll discuss in the later slides. Yes, what it infers from rect. Rect is nothing but it is a rectangular shape and the 4 coordinates of that particular rectangle. So 7 to 8 low track libraries are for area efficiency. So there are different types of I mean to say the left files or the tech left files depending upon the application of your output module or the integrated circuit that you want to develop. You can choose the library according to you that is given from the foundry. So usually the libraries will be segregated depending upon the tracks. Now here a 7 to 8 track libraries are used for area efficiency. Now if you want the area as your the main attribute, that means you are developing an chip or ASIC implemented circuit where area is mattering, then in such case you can use this particular track library, that is 7 to 8 low track libraries, and usually 11 to 12 tall track libraries are for performance but have high leakage power. So you need to compromise with any of the things. If you it is an area dependent, then you need to compromise with the power. So if it is a power dependent, then you need to compromise with area. So it's vice versa. So it depending upon the application, you can choose this type of libraries or the type of track of cells that you can use. And these are just the examples where you can use this particular tracks. So usually 9 to 10 standard track libraries are for reasonable for area and performance. So when area and performance are both your constraints while developing an integrated circuit according to the customer whatever applications they have given. So if area and performance both matters for developing your chip, then you can just use this 9 to 10 track library. So what a technology left description, I mean to say what a tech left consists of usually is list of metals available for routing. That means you need to interconnect with some other cell, right? So that particular interconnect information of that cells defines the units and design rules. So how much metal width you need to use when you are using that particular technology library. So this width, spacing and pitch for the layers depends upon the technologies, uh, name and number conventions of that layers and vias. So layers are nothing but the metals. Via is nothing but when you have a type of metals, different type of metals. So you have metal 1 and you have a metal 2. Now you need to connect metal 1 and metal 2. So directly you can't jump off while using the same metal. You need to have a medium while connecting from metal 1 to metal 2. So you use a via object or a via cell for that particular connection from metal 1 to metal 2. So when you're jumping from one metal to other metal, you have to have a medium or a cell called as via. So that particular cell is called a via cell. So the information regarding that particular via cell also will be mentioned in the teclef itself. So the physical and electrical properties, those are nothing but the resistance and capacitance values and the width or attributes of that particular cell also should be mentioned, will be mentioned in the teclef files itself. So example for this physical and electrical properties are the direction, pitch, uh, width, offset, thickness, resistance, capacitance, and the maximum metal density, antenna rules, blockages, and the design rules. So the manufacturing grid definition. So this is one of the physical attribute again, which will define the manufacturing while it is going to the manufacturing. What are the grids it has to route on, or what is the area unit it has to route on when it is going to the manufacturing, that will be defined using an attribute called as manufacturing grid.
Shravanti, not audible.
Okay. Is it audible now?
Yeah, it's now it is okay.
Yeah. Yeah, sure. Okay, so the site unit tile definitions that can be used in rows so that the placement engine guide placement of the cells. That means how much area it has to contribute when it is connecting to a cell. That particular information is defined by the unit tile or the site information of a metal. And these are all the electrical properties, that is length, capacitance, resistance, power, and the technology precision of that particular metal. So I'll just show you an example declaring what are these attributes. So the technology left file contains the simplified information of the technology for use of placement and routing. So names of that particular metal. So according to the library file that you have chosen from the foundry, the tracks will be defined. So the tracks defined according to the library we'll have some naming contribution, because we have to see the change of the metal that you are using from one metal to other. So the name of each and every metal will be defined some way in such like M1, M2 and M3 according to the number of layers that you have chosen. Next is the layer type, such as routing or cut means if the type is cutting, then it's a VR cell. Electrical properties, those are nothing but the resistance and capacitance values. And the design rules, those are the minimum width, minimum spacing that particular interconnect have to follow while it is going to a placement and routing stage in the physical design. And the antenna data, so there will be some rules in the manufacture from the manufacturing side. As I told you in the introduction session also, there will be a file where manufacturer gives some rule deck. So one such rule is the antenna data. That means just take an example. One, I'll just project you an example. One, if you have a cell, just take an inverter itself. Now, the metal, if that is getting connected to this particular cell, that means the interconnect that is getting connected to this particular cell, how much length it has to maintain and how much width it has to maintain when it is going to connect to this particular cell. So one of the antenna rule is it has to maintain some minimal length when it is connecting to the input of the cell. So some such kind of specific rules will be mentioned in the antenna data itself when you consider a left file. So this is one example. The metal that has to be connected to a gate, how much width and spacing it has to maintain so that it will not be facing any issues while it is going to manufacturing. So such kind of rules again will be contributed in this particular file itself. There are so many set of rules that is not required for you, because as of in synthesis stage, when you go to physical design and implementation, more such rules comes according to the rule decks of that particular technology. So, and preferred routing direction. So if I have a metal 1, so I have a metal 1, if my routing direction that is designated in my left file is horizontal, that means that particular metal should be used throughout my design in the horizontal direction itself. Now these rules are again from the manufacturer perspective. You should not change the metal direction. That means if a metal is designed for a horizontal direction, you should not route it in a vertical way. You should use the same routing attribute whatever is specified in the technology left. So the preferred routing direction that interconnect have to use will also be mentioned in the technology left file itself. So site, the X and Y grid, those are nothing but the X and Y axis of that particular metal. Core sites are the minimum of the standard cell. So these are again same as the sides of the particular standard cell. So a particular metal can have a single height track or a double height also. So if I tell there are some 2 to 3 tracks passing on that particular cell, metal tracks again. So this particular standard cell is not designated. That means throughout the library, all the cells need not to be occupied only 3 tracks. It can occupy the multiple tracks also. It can occupy the 6 tracks, or it can occupy a multiple of 3 also. So it depends upon the technology left file that you have chosen. So depending upon the application, it is not like for your design you need to use this. It again depends upon the application that you are designing it. IOs of that particular special site. So what are the input and output metal attributes that you need to use for that particular metal, and via definitions, those are nothing but the intermediate metal informations when you are jumping from the metals, and the units of that particular metals, grids of that layout and routing. So in which particular coordinates or in which particular points that metal have to route its interconnect, that and all will be defined. So this is an example how a technology left description of a metal looks. So the layer is metal 1. So for a metal, the type is routing. So as I told you, if the core is routing, that means it is used for interconnect. The pitch is nothing but if I have a metal M1 and if I have a metal M2, or it might be the same type of metal also. Now, there will be a center line passing from this metal and there will be a center line passing from this metal. What is the spacing that it have to maintain from center of this particular metal to center of the other metal when it is parallelly passing, or when it is I mean to say horizontal way also, or in a vertical way when it is parallelly passing? The center to center spacing between that particular metals is defined in the form of pitch. So is pitch clear? So pitch is nothing but the center to center spacing of a metal. So the width that particular has metal has to maintain while it is interconnecting with a cell, and the direction. This is very important. So it has to route only in a horizontal way, and the resistance per square unit, this is defined in some value, and the capacitance per square unit. So for square unit of metal, it has to implicate this particular resistance and capacitance values. Anyway, this will not be taken from this file. There is another file also, but to start off, when you are using and physical information, these values are much important. So for each and every file, these are the for each and every metals, these are the some important attributes that a left file will contain. And in the same way, for a via cell, so layer via and the type will be cut. So if the type is routing, that is for interconnect. So if the type is cut, that means it will be for a via cell. That means when it is jumping from one metal to other metal, you need to use a type of cut cell, that is a via cell. So the type will be defined for that particular cell. In the same way, the coordinates of that cuts also will be defined. So this is an example. So one of you guys were asking what are the units. So these are the units. First, in the techlef file, the unit section also will be defined in the file. So this is the version of the tech file, and divided by character for that particular, and the units throughout the database. That means throughout that file, whatever number values you are giving will be mentioned in the unit section of that particular file. So database is microns. So 2000 microns, that means a value is there if 0.065, this particular value will be multiplied by 2000 microns throughout your left file. So it is something like that. So the units of that particular values mentioned in your file will be also given, and the manufacturing grid is 0.05. So it is nothing but the grid, the coordinates it has to follow. Now you have a chip. Your chip will be segregated into smaller units called as manufacturing grids. So this particular manufacturing grids will be following your metal layer. So that grid values is mentioned in the manufacturing grid. So before entering into the actual metals, there are some poly and oxide metals also that are needed to be for the implementation. Directly, it has to not contact with the implementation metals. There will be some poly metals and oxide metals before starting off with the actual metals. So that particular metals also will be defined. These are all the layers that will be enabled only when you are going for manufacturing. But when you are in synthesis stage, this particular metal layers will be commented. But if you are going for the manufacturing stage, this have to be enabled, because there you are checking the implementation of the complete circuit, right? So that particular type is defined by master slice. So these are all the oxide layers of a metal. Now, this will be the actual implementation. So this is the actual example of how the metal, as I defined before, spacing, width, pitch, horizontal and offset, resistance, capacitance, everything will of a particular metal will be defined in the same way for the VR cell also. So this is an example of the interconnect information file or a technology left file. Now, usually in the industry, there will be a metal stack defined in your left file or a technology left file. That is a tech file in the synopsis attribute. Now, if you take a 3D view of that particular metal stack, so the metal stack will be defined with this attribute at the starting section of your tech left file. That means 12M, 4X, 6Y, 1Z, and LB is for bump. That is the other thing. I'll discuss what is it. So that means here in your technology left file, uh, 12 metals should be used. That means totally 12 metals will be contributed for the complete usage of the circuit. So 12M means 12 metal layers. Among the 12 metal layers, 4 will be used in x-axis or the horizontal direction, and the 6 metal layers, that is from M5 to M11, will be used in y-axis, that is the vertical way, and z-axis is nothing but a 3D view of, if you can see, if so this axis in this way, some 45 degrees angle when you take a 2D diagram. So that particular metal can be used in the z direction. So this stack, whatever 12 metal, 4x, 6y, 1z, and the lower is bump, will be defined in the teclef itself. So according to that, the complete metal size and which metals you need to use for routing in horizontal, vertical, and in z direction will be defined according to the stack. Now, what is bump is, there will be some power sources in your design. There will be some power ports. Let us take whatever power source you know as of now is a VDD power source. Now, this VDD power source will not be connected directly when it is going to manufacturing. It needs some source of metal through which the power source can be fluctuated. So that power source or the power pin of your module is connected to a metal called as bump, so that through that the outer voltage, whatever you are giving as an input, can be contributed into your internal circuit. So you have a circuit. Now you have a pin called VDD. This pin will have an extension metal of a metal called as bump. Okay, so this bump will be used for this VDD power source fluctuation. So that is nothing but bump. So this stack is given by the foundry itself. And the orientation, this is very important. Orientation is defined in two cases. One is HVH and one is VHV. So what is HVH is, let us take an example. Your circuit is having 9 metals. Now, if you are choosing an HVH algorithm, That means amongst the 9 metals, metal 1 will be your horizontal, metal 2 will be your vertical, and metal 3 will be again a horizontal. That means it is following an HVH algorithm. In the same way, if it is a VHV algorithm, that means your metal is starting with an orientation of vertical. That is, metal 1 is vertical, metal 2 is horizontal, and the metal 3 is vertical again. So it depends upon the algorithm that you have designated in the tech-lef. Here I just projected an example. As I told you, you can see when you're jumping from one metal to other metal, you have some set of cells called as via cells. So these particular metals, where you can see the connection between two different metals, is called a via. So there might be no a single via, there might be a group of vias also. If you are having a group of via, then it is called as an array of vias. So here you can see 3 cross 3 is my array size. So 3 horizontal way and 3 vertical way. Here it is 1 cross 3. So 1 is my horizontal direction and 3 are the number of vias in my horizontal direction. So this and all are just an example when you see it in a physical view or a layout view when it is connected for the circuit. So, while going for the physical implementation,
Can you repeat LP? What is LP?
okay, so
Bumper.
yeah, so there are, as I told you, if you are having a metal stack of 12 metals, among these 12 metals, the power connection will not be used. Like I mean to say, if you are having BDD pins in your netlist or in your circuit for that particular cell, this metal stack of 12 will not be used. There will be some other metal called as bump metal, where you can use only this metal layer for the power sources. So specifically for power sources, if you want to fluctuate this power for the outer world, so you have a voltage source, you have a circuit or a chip, you have a VDD source coming somewhere from here. Now this VDD source have to be connected to the VDD pin of your module of your gate level netlist. Now this have to have some metal connection, right? So this metal connection will not be taken by the metal stack, that is metal 1 to metal 12. There will be some separate metal that is nothing but a bump metal used for power connections. Is it clear?
Cleared. You go ahead.
Yeah. Now as a backend engineer, while going to physical implementation of this metals, when you're doing physical design, usually as a backend engineer, this are chosen as the metals. So top metals are used for power. When you're considering full chip, it will be a bump. When you're at a module level, usually the top metal layers will be used, that are metal 10 and metal 11. And for clock, for whatever clock interconnects are there, that means your clock port interconnects or clock metals will be taken care by the middle metal layers. Those are M6 and M9. And the data, that is D pin, Q pin, of that particular cell, if I take an example of a sequential cell, the data pins are D pin. So that particular layer interconnection will be taken care by the metals of metal 2 to metal 5. Those are nothing but the lower layers of my metal stack. So this is predefined. If you are a backend engineer, you need to use this particular layers according to your application. So there were some rules in the techlef file, right? So what is spacing and what is this minimum pitch and all. So these are some diagrammatic representations of this particular metals. So minimum spacing is nothing but, so if you can see metal 1 and metal 2, sorry, metal 1 and metal 1 are parallelly passing horizontally. So what is the spacing that it has to maintain between that two metals? So that spacing is mentioned in the tech left. And in the same way, a via to a metal. So if this is a via, so one metal 1 to metal 2, it is jumping, it is using a via cell. So a spacing between metal 2 and this particular via cell also will be defined. And this is a diagrammatic representation again, where you can see a via without stack and with stack. So if you have a metal jumping process happening parallelly, that means it is not overlapping. VI is not overlapping one on the other. It is taking some spacing and it is creating a via to jump to the other metal. So in such cases, we don't call it as a stack via. When it is creating vias while jumping the metals at a same place, that means it is called as stack. So this is just an example where you can see via without stack and with via stack. So you can see whatever rules I have specified in the previous slides will be in the layout will be displayed something like this. So here I just took an example of widths and spacing of the same metal and the different width metal also. So what rules specifically will be defined is, if they are parallelly passing of same width, what should be its spacing? And if width of the metal is different, that means if there are two different types of metal widths passing parallelly, then in such case what should be the spacing that should be followed in that scenario? So that and all rules will be there. Now there is a metal and metal passing. So this is the usual or the normal spacing rule. And when a metal is passing and a metal with via is passing, how much spacing it has to follow? And when two metals having vias are passing parallelly, what is the spacing it has to maintain? So this particular spacing rules also will be mentioned in the techlef file itself. So I think is it clear with the techlef and the standard cell gate left file, so that we can move on with the next file? Okay, so in the 2D view, it is very difficult that I can show you the Z direction also. Usually, if you take a 3D diagram or anything, you will be having three directions. One is horizontal, one is vertical, and one is a Z direction. Usually, three axes will be there. So, when you go to the manufacturing process, there will be some metals defined that have to be routed in the Z direction, or when you take a 2D view, it will be a 45-degree angle again. So in what direction it has to map or it has to route another gate, that particular is designated by a Z direction. So Z is an other direction when you are considering a 3D layout view. More any queries, or shall we move on to the next file?
Please, you can.
Okay. Now the other file, according to the inputs that we have designed, is one more extra file. One more extra file is a QRC tech file, where you see already I mentioned, like you will have some resistance and capacitance values
Excuse
in
me.
the tech left itself. Okay, there is one query. Yeah.
Sorry. Actually, you mentioned the antenna size and antenna data size in standard cell library. What does mean that? Antenna size.
Okay. In the left file, I just took an example, right, of a gate. I just showed you a projection where a gate is have to have some metal getting connected to that particular gate. Now, what should be the length of this particular metal? Okay, which is getting connected to that gate. So there are some sort of rules called as antenna rules, where the metal attached to the gate, when you go to that particular transistor level, how much spacing that particular metal have to have, how much length it has to have, will be defined in a form of antenna rule.
It is for input and then output pins.
Yeah,
Is it correct?
any of the pins, any of the pins.
Okay. Okay.
Yeah.
Thank you.
So I stopped where, okay. I mentioned in the tech left also you will be having some resistance and capacitance values, but those values will be varying when the net length changes. That means a standard cell left or a routing left cannot be designating or cannot be giving an actual values when it is going for a physical design implementation. So there is a separate file where you can see the resistance and capacitance values based upon the length, width of the metal that is used for the interconnection. So that particular file is called a QRC tech file. So QRC is nothing but Quantus is one of the tool where they extract this RC and capacitance values. So it is basically elaborated as Quantus resistance capacitance tech file, technology file, and this is also again provided by the foundry itself. Now, what does a cap table contains is, or a cap table file or a QRC tech file contains is, the resistance and capacitance values which are used to model interconnect parasitics of the design. So here you can see an example. Two inverters are connected back to back. Now, in this case, this particular wire is used for the interconnection. Now, if the length of this particular wire is this much, let us take 0.1 microns. Now, what if the length of this particular interconnect is 0.1 microns, what should be my resistance and capacitance values? So that particular resistance and capacitance tables will be there in a cap table file or a QRC tech file. So usually this particular file is compiled or generated from a file called ITF file, that is nothing but interconnect technology format file. Usually uses this physical parameters such as layer thickness and the dielectrics of the metal. So this extraction of the QRC file that will be given by the foundry is compiled using this file called ITF file. So as I told you, there's a tool, Cadence QRC is used to compile ITF file, and this is converted data into resistance and capacitance values, and by which they write a file called as QRC tech file. So basically, this is again implemented when you, I mean to say, this is useful when you are going to post production, that is nothing but when you are in the manufacturing stage itself, because at that stage itself you will be knowing actual location of the gates, actual interconnects of the gates, and according to the previous applications and all, they just put that circuit in a ITF file, or which is a binary format file, and they compile it using a tool called QRC tool, so that if the net length will be this much, what will be my resistance and capacitance values will be used same according to the technology. So for 45 nanometer, just take an example. They implemented a circuit and it is occupying, if the length is 2 centimeters, it will not be 2 centimeters, but just an example. So if the length is 2 centimeters, and it is occupying some resistance value of 0.1 ohms, and it is occupying a capacitance value of 0.2 picofarads. Now, throughout the 45 nanometer technology, if the length of that particular wire is 2 centimeters, that means the resistance and capacitance value throughout the circuit will be same. So this was again done by the multiple iterations only. So they have developed this cases because this resistance and capacitance values are affecting again the timing and power also in indirectly. So they created a file called QRC tech file where they can mention the resistance and capacitance value before itself if my net length is so on. So they can not face any issues with the power and timing in the later stages. So this is what a QRC tech file is. So ideally, QRC tech file is made available from the foundry itself. So it is an again standardized input that will be given by the foundry. Now, what is a so usually the resistance and capacitance table will be looking something like this. So if you take a capacitance table, it is very important. So here it will have some list of capacitances values as such. One is the coupling capacitance, area capacitance, and the fringe capacitance. So these are the attributes if you would have heard in VLSI subject also. Coupling capacitance is nothing but when two nets are parallelly passing. That means it might be horizontally or vertically. So what should be the capacitance value when it is parallelly fluctuating? What should be the capacitance value between these two nets? And the area capacitance is if this is occupying this much area, what should be the capacitance value? And fringe capacitance is if there are non-overlapping happening. That means a metal is passing horizontally, parallelly a metal is passing in a different direction. So the capacitance in such cases is called as fringe capacitance. These are again the dielectrics when you go deeper into the subject. But as a user or a new to the subject, you can just get to know these are the list of capacitances usually a cap table file will be having. So the other extra physical input that we have is the physical def file. Def is a design exchange format file. So the extra input mainly when we are doing physical synthesis process is a def file. So what is a def file we are giving here is, so there is a stage called floor planning. When you go to physical design, there is a stage called floor plan, the first stage of physical design. So in that stage, we do the placement of pin objects of your gate level netlist and the memory objects of your gate level netlist. Now, what this floor plan def file contains is, if you have a floor plan information, so my pins are placed somewhere here and my memory objects are placed somewhere here. So I have this much of vacant area where my gates can be placed. So gates will be placed in placement stage. But when you are in floor plan stage, you need to know when there is a gate count of millions and trillions. In such cases, area is not a compromising factor. So you should not optimize your gate level netlist in a broader way, or you should not optimize the gate level netlist in a huge number. So in such cases, this def file will be used for that particular physical synthesis information. And the advantage here is we will get to know the area that is vacant, so that according to that area, the gate level netlist can be optimized. So when you're doing logical synthesis for the same design, just take an example, it would have optimized a huge number of gates. Now you give a tool an extra input called as def file, that is a design exchange format file of a floor plan. Then it will get to know, okay, I'm having only this much of vacant area. I need to reduce my gates according to this area, and it will I mean to say, it will use an algorithm of physical synthesis, and it will optimize the gate count according to the vacant area that you have specified in the def file. So this is a def file information that you will see in the demo also, like how it looks and all. So clear with the def file. So basically, it contains the following information. That is the macro, that are memory information, I/O ports, the size of the block, how much area it is utilizing for the memory objects, and the die size is the boundary of that particular area. Blockages, if any. That means in a particular area, if some cells have to be not contributing, so in such area we put a blockage. These are all the physical design objects, and the fences also some placement blockages. So this all information will be mentioned in the def file or the design exchange format file. So here is the cadence flow of synthesis while you need to use this sort of commands when you're doing it in a tool. So here you can specify the efforts also. The first step is you need to set the design name. Same, how did you set for this logical synthesis? Next, you need to set the efforts while it is doing generic mapping and optimization. So according to the application, you can set the attributes like high, medium, low for the efforts while it is doing conversion of generic mapping and optimization. So this particular commands are for the setting of efforts while it is converting to the gates. So this particular command where you can set the directories, set a date. So when it is converting into the gate level netlist, usually in industry they write some scripts setting the date format and the output and report format. Because it's an iterative process, they can make it out easily at what time it is generated, so that you can parallelly check the outputs according to the date and time it has generated the gate level netlist. Now, here using this commands, you can set the paths of libraries and the scripts or the RTL files that you want to synthesize. So these are all basically when you want to load some inputs and all, these attributes are basically used. And the library settings, same, how did you read the libraries? Here the command to read the library is setDB library and the library name. And here we are giving an extra input also, that is left file, the physical input library file. So to read that file, set underscore db left library is the file and the file name. And to read the capacitance file, that is the QRC text file, you can use a command called set underscore db cap table and the file name. And read def is the command where you are reading an extra input, that is the floor plan def file. So read def is the command to read the def file. Now here floor plan def is a user generated file. It will not be given by the foundry. So when you're doing demo, just make sure like you need to have a floor plan def that will be done by the user itself, not from the foundry. Now in the same way, we need to read the HDL, we need to read the SDC, and we need to elaborate the design like how we were doing for logical synthesis. So the same steps should be followed. Now, what is the extra command we are giving is, we will just mention the tool to perform this generic and mapping and optimization in a physical way. So that list of commands, I'll be showing it in the demo. Now, clear with the set of files, whatever I have discussed, so that I can move on to the demo.
Hello.
Yeah.
Ma'am, coming to from the logic synthesis, like if we already we have optimized some part in logic synthesis, right?
Yes.
So coming to the physical synthesis part, how it will be optimized? Means if I have 1,000 cells and I optimize it to 700 cells, so in the optimized of using the physical synthesis, that 700 cells again optimized, or what? How can we say optimization there?
Okay, let me show you in the demo. So how is it optimizing? You'll get a clear idea.
Okay.
Yeah. So you have done a logical synthesis for the UR design, or I have shown the demo for this particular UR design. So I have took some complex design where you have an interface of APB with I2C. So here I just took the run article that I have used for logical synthesis. So here, these are the attributes. Eitherwise, you can use for logical synthesis in the form of, this is basically the industrial flow. There will be some attributes you will be mentioning with a command called setDB. So you can just do man on this setDB and get to know what are the library attributes. So this is the attribute that you are specifying for giving the path of library. So these are the physical library path according to my PC. So this path will be varying. Again, I told you the command also previously. You can just do pwd where the library file is, and you can just copy paste that particular path. In the same way, to set the path of RTL file, the command is this. So setDB init hdl search path is the command. And now, with these two commands, you have given the path of that particular files, but the tool have to know, going to that particular paths, what is the file that it has to select. So in this particular library path, it has to select slow.lib. There is a file called slow.lib. It has to select that particular path. So using this attribute, we call the files in that particular path. So setDB library slow.lib is my library file name, and fixed2.left is the left file, and cap table is the capacitance or the QRC file I'm loading, and HDL is nothing but I'm reading my RTLs. So elaborating is I am linking the logic with the input and outputs. So check design unresolved is if you're not reading any RTL files in the read HDL, so it will show an error for that particular RTLs. So next is we need to read a timing input also. The other is read SDC. So read SDC is the command for reading the SDC file. So syn generic, syn map, and syn opt are for 3 steps of synthesis, translation, mapping, and optimization. So this is the same file, but with an industrial flow or industrial commands that I am showing you for the logical synthesis. Now, for a physical synthesis, what are the extra inputs that we are loading is we give the physical library as usual, and the capacitance and capacitance table, that is RC file. And now the extra input here is we are just reading the floor plan def. So floor plan def I have already generated from the for this design in the Innovus tool. The tool for generating this floor plan def is Innovus. So from that particular tool, I have already generated a def file, that is the floor plan information file. And now when you're doing physical synthesis, you need to tell, that means you are doing the physical synthesis right. So the switch you need to give for each and every process of conversion is you need to give a switch called hyphen physical for 3 steps of the conversion. So syn generic hyphen physical, syn map hyphen physical, and syn opt hyphen physical is the command for conversion of gates. So this is the basic flow you need to take care of while you are doing the process of physical synthesis. Okay. Now let us see the running of these files. Okay. There is some question. Okay, so now let us open this left file and def file so that you can get a clear idea how it looks. You'll have a directory called CAD. Inside that you'll have Foundry, Digital, 45 nanometer, LITs. Inside that you'll have a LEF. So fixed 2.left will be your left file used for the cells. So this is how the left file was there in the example. Also, you can see the unit section, and if you can see, so for each and every metal, the direction, the type, pitch, width, area, and the spacing tables will be mentioned. So these are some extra attributes, but these are not so required for you. So for the VR also some attributes will be defined. These are in the case of TechLef. So wherever the information regarding the metals is there, that and all information is called as a TechLef information. As I told you, in this file itself, in the cadence properties, you will be having the physical information of the cells. If you do Control F, you will you will get a search bar, or else you can just click from here for the searching. I'm just searching for a cell called AND. I'll search for a cell called buffer because AND. Okay, so we can see for a clock buffer, this and all attributes are defined. See, the rectangle is nothing but the box areas of that particular pin Y. So buffer is clock buffer is this particular cell which accepts clock as an input at an A pin or the input pin of that buffer cell. So as defined in the theory session, the attributes for this particular cell will be defined in this particular file itself. So remember the file name. So the file name is this fixed 2.left in this particular directory structure. So it will be in home CAD Foundry digital 45 nanometer, and libs inside lib there will be a left directory. So remember this path, and the file name is this file fixed 2.left. So this is how the left file looks. You can just go through this file, and if there are any issues, I'll just clear that doubts in the next session. So once if you look, you will get an idea. Now, the next file I have used is the def file, where I have the floor plan information, that is my core information or my pin information, and if there are any memory objects, that memory objects placement information will be available from the def file. So I'm just going to that particular file. So here you can see the floor plan def. I'm just opening that file. So what and all information it will be containing is, so it will contain the information of that particular pins. So for this design, I totally have 107 input and output pins. So for that particular 107 input and output pins, what are the metal it is using, what is the direction, and what are the type of routing it is using, that is signal or clock. So for each and every pin, the direction and the type of metal it is using will be defined, and I'll mention it again. It is a tool generated file itself. So this is how a floor plan def looks. This is generated from the physical design tool, and the row is nothing but I told you, right, in the core area you will have some rows. You'll have some rows in a particular area where the standard cells have to sit. So the standard cells or the gates only have to occupy the areas within this rows. So that particular row information of that complete area will also be mentioned in this def file itself. So this is how the floor plan def file looks. The other physical input we are giving is a capacitance table file that is there again from the foundry itself. You can just select the path from the foundry. So it will be in home directory again. So inside home, inside CAD, again you'll have a foundry directory. Inside foundry, you'll have digital. So I'm just choosing 45 nanometer. You can choose any of the libraries. So inside libs, you'll have a cap table directory, capacitance table directory. Inside that, you'll have two conditions. One is best and worst. So you can choose any of the cases. So I'm just opening a worst case cap table. So you can see the resistance and capacitance tables will be defined. So these are all the resistance and capacitance values according to the widths and according to the spacings of that particular metals. So this is how a cap table looks. You can see from your side also, you can just go to that path and open this particular file so that you will be clear with this file also. Now, these are the extra three inputs we are getting included once we are entering into physical synthesis part, and this will be the run.tcl file or the running format file to generate a gate level netlist. Now, here I have already generated running this files. So, uh, in the last session, I was showing you command by command, right? So, I was executing command by command. Now, I'll just show you an alternative to how to run the file. Now, in this case, I am just implementing. So, I'm just showing you the logical synthesis part here in this case. So, is it visible or should I maximize? Okay. Now, once you are entering the tool, that means you are inside genus. If you want to exit the tool, you can just give them command called exit so that you will be out of the tool. Okay. Now you are out of the tool. Now here, if you want to invoke the tool, just give genus. That means you can enter the tool. So from here, I think you will be able to invoke the tools. There is no need that you need to source the CSHRC file. Now, once this warning comes something like this, that means you are inside the tool and you will be seeing some symbol with arrow mark. So here, if you want to run the complete file at a time, so you can just give a command called source. I think I've discussed this in the previous session also. Source run.tcl is my tcl file name or the file of the commands file name. So it will do the complete process of conversion of gates, that is synthesizing in the logical form. So it will take some time to run. If you can see, run.tcl is my logical synthesis file and run_physical.tcl is my physical synthesis format file. The difference is we are just reading a def file and we are giving a switch called -physical while doing this process of conversion into gates. So it is optimizing. Now, here it has done optimization. Now let us see the gate count so that once it is performed physically, that means once we are doing physical synthesis process, how much it is designating for that area. So I'm just doing the command called report_gates. So it will show the gate count. So for this process, I have a gate count of 1271. That is approximately 1K gate. Now, here in the physical synthesis, in the other terminal, I mean to say, I will run a physical format file or a physical synthesis run.tcl file so that we can see a change of the gate count when you are doing physical implementation. So here again, I'm exiting the tool. Now here I'll run a file of physical synthesis. So again I am invoking the tool genus. For the same RTL, we are just giving an additional input of I mean to say the def file and the physical format information of conversion, so that we can optimize a few number of gates. But this might not implicate so many gates, but when you come to industry, there will be some more number of logics coming into picture. So in such cases you can see a huge number of change. Now here I'm just sourcing the physical run.tcl file. So source, the file name is run underscore physical.tcl. So it is doing the physical synthesis process for the same design. So remember the gate count, previously it was 1271. You can see the changes in the power and in the area you can't see because it is not physically implemented. You can see the changes in the power also. And in the logical synthesis, now you can see area also, because in this process of logical synthesis, we have included a physical format file also. That is nothing but a left file. So that's the reason here it is showing me the physical area that is going to occupy for that particular cell. So I told you in the previous session also, there is a command called power report underscore power. If you execute that, you can just see the power occupied by that particular logic. So this is the power format. So this is the leakage power. This is the dynamic or the switching power and the total power. So physical synthesis usually takes some runtime more, because we are giving some extra input. We are giving some extra input called as floor plan def. So it has to invoke the Innovus tool to accept that whatever floor plan def we have given. That's the reason when you're doing physical synthesis process, the runtime will be more when you're comparing with logical synthesis. So I did not execute the gate command for physical synthesis. I don't think so. I showed this gate count. So here, once this physical synthesis process is done, now let us check what is the things it has optimized. So report underscore gates, I am doing it again. So you can see now my gate count is 1264. Here my gate count was some 1271. So it was the gate count that it was able to optimize when I am adding a floor plan def. So here it might be a less number, but when you go to complex designs, it can optimize up to some 200 or 300 gates also when you take a real-time project. So in this way also it is helping me in a few way, because some 10 to some 8 gates got reduced when you are going to physical synthesis. I told you in the previous session also, physical cells are some cells. When you do physical design, you'll get to know there will be some cells called well taps, end caps. Those are not functional cells. According to the application, that particular cells will be added in the floor plan. But as of now, I didn't add any physical cells in my design. That's the reason physical cells are 0. I did not add any application perspective cells or the end cap or well tap cells in my design. That's the reason physical cells are 0. Those are not logical cells. That means it will not be having any functionality. It will just have some application. Take an example like well tap cell. That particular well tap cell will be used for avoiding latch up. So it is only used when there is a latch up in your cell. So as a starting user, you will not be knowing what is latch up and all. That's the reason I did not mention any physical cells in my floor plan information. That's the reason physical cells are 0. So this is the optimization change you can see when you're implementing your process physically and logically. So you can get registered for this physical design course so that you can get to know more about this physical cells and all, how to add those and all. I can show in the GUI itself. That's again a other topic. Okay, any doubts regarding this flow I will address. So I think I am almost done with the complete flow. So any queries I'll address. Okay, not able to see the files accessing the tool because there's no file. Okay, what is your name? Okay, Venki. Okay, so there will be a path. I'll just tell you that path. So here I have used a path of like home, inside home. I have a directory called CAD, right? So if you're not having a directory called CAD, you will be having an alternative directory as install. INSTALL. So instead of CAD directory, you will be having a directory called as install. So you can just go with the same path, except in the CAD place, you just replace it with install so that you can see the files. I think your library files will be there definitely in this install directory. Okay. Can we go do directly physical synthesis without doing logical synthesis? Okay. So for doing physical synthesis, you want a floor plan def. So a floor plan def can be generated when you have a logical synthesis netlist itself. So for generating a floor plan def, one of the input you need is a logical gate level netlist or a logical synthesized gate level netlist. So that's the reason you have to do logical synthesis, then only you need to move to physical synthesis. Without having a logical synthesis gate level netlist, you can't do floor plan. So you need to do it once it is done after logical synthesis itself. Okay, so what is effort is now okay, let us take an example. We have a complex design. That means we have some billions of gates. Here, my gate count is just 1K. So it is not so complex design. When you go to real time, there is some command in the tool where you can set the efforts for the synthesizing process. So here there is a command in the tool set mapping effort or set synthesizing effort, where you can set the efforts for each and every stage of translation, each and every stage of mapping, optimization as to minimum, high or low according to the application that you want to, or according to the engine that you are running your synthesis. So when there is a complex design that is usually taken care in industry, you'll have some effort attributes. So I'll just do some commands called help star effort. So you'll get to know what are the commands which are related to effort. So if I'm doing this help star effort, that means I will get to know all the commands which are related to effort. So here you have some command or attribute set synmap effort. So I'll just show you what is this command doing. So I'll just do man. That means it will show the description of what that attribute is doing. Now, here what this command or attribute basically does is specifies the optimized effort to use the synmap command, and this option usually provides feasibility and analysis by performing quick synthesis of the design. So for this attribute, you can design three variables, that is high, low, and medium, or express or none. So according to the application, you can just use this command when needed. So as of now, I'm not using because it's not so complex design. It's just 1K gate. I can take it forward. So while it is mapping, while it is optimization, you can set this efforts according to the strength that you need for that gate level netlist.
Then what is the difference between high and low? Means for high the optimization will be high and for low the optimization will be low, like that.
Sorry, I didn't get you. Can you repeat?
Actually, what is the difference between then high effort and low effort? For high effort, the optimization, if I am using high effort in that optimization command, so the
Yeah.
optimization of the gate level netlist will be high. Or if I am
Yes,
using
yeah,
low,
obviously. That is what I mean to say. When you're using high, that means it is putting more efforts. It is putting more efforts to optimize gate count. I mean to say it might be in terms of power, it might be in terms of performance or timing. It is putting more efforts. When you're giving low, that means you're not bothering about optimization. If it is a gate count of a minimal number also, it is fine for me. So you're giving a tool engine to undergo the process in such way. So high is nothing but you are putting more efforts while doing optimization. You are putting more, I mean to say, according to the algorithm the tool have set, you can define an attribute high. You are telling the tool optimize to a higher level that you can optimize. Okay. More any queries regarding this physical synthesis? Okay. Okay, what is cap table? So I think I gave a clear idea. So if it's also, so I have a gate. Now my gate is interconnecting with some other gate using some particular net. Now, for this particular gate, if it is interconnecting using a particular length of this metal, what should be the resistance and capacitance values of that particular metal which it is using for interconnection? So that resistance and capacitance value information will be there in a cap table file. Yeah, VCD file is generated. So as I told you, it again depends upon the application. You are taping out your chip or you're manufacturing your chip. If your application is for a power oriented application, in such cases, you can include an VCD file. So how to read that file? I'll just tell you. If you have that VCD file, while writing out that VCD file when you're implementing the Verilog, there is an option called read underscore VCD in the genus tool itself. So using this command and the path of that file and the name of that file you can give here, and you can just read that VCD file also. So read underscore VCD is the command for reading the VCD file. That will be only taken care when you are taping out for an application of power oriented chips. So as of now, there is no VCD file I generated. So you can use also with a command called read underscore VCD. Okay, how to generate a def file. So usually in the Innovus tool, it's a long process again, but as a user, I'll just, because it is a synthesis process itself, right? We are not getting more into this physical design. I'll share this def file also so that you can just see the change. It is again a long process. You will have to have some physical design inputs for that. It is not a small process so that I can show you here. It you have to know what is floor plan again, what are the inputs, what is globals, what is view definition, what is MMMC. So there are a lot of inputs again. So it is generated in usually in Innovus tool. Okay, so is cap table provided by Foundry? Yeah, it will be there in the Foundry itself. So I have showed you the paths, right, in the run.tcl file, or else in the Foundry itself. I'll just open a parallel terminal. So I am just entering into that particular path so that you guys can make it. You guys can open that file and see inside home. You will be having a CAD directory or install directory, but as of now I am having a CAD directory. So inside CAD, I have Foundry. Inside Foundry, I have digital. Inside digital, I have 45 nanometer. Inside 45 nanometer, I have lips. I think it's visible. So inside lips, I have a cap table directory. So inside cap table, I have two cases, worst case cap table and best case cap table. So this is again what is worst case and best case. I will tell you in the SCA sessions. But as of now, in synthesis, you can use either of the case file. So I'm just entering into worst, and now I am in worst directory. So cd is the command to change to that directory. So cd is nothing but change directory. If you want to enter that particular path, you can give cd and that particular path. Now here, if you do ls, that means if you do listing of that particular directory, you will get to know what is the file name. So you can just give gedit. Using the terminal access, I am giving you the things. So gedit and the cap table. So you can see that particular cap table file. So it is given by the Foundry itself. Okay, as I told you again, you as a starting user, you use either best or worst. I start off with SGS sessions, I will tell you what is the difference between worst and best. So cd is basically command for changing the directory, and to open that particular file, you can just give the command called gedit. Okay. More any queries?
Hi. Do we have any notes on power?
Hello? It is not audible. Can you be a bit clear? Okay, so there is one question. How will we insert scan cells during DFT? So any design will be usually implemented in two forms. One is functional mode and the other is scan mode. So it depends upon the application again for the manufacturing process. So there is an other script where you need to run to insert the DFT cells or the scan cells. So there will be scan insertion attributes in the genus tool itself. So you can just do help star DFT. in the genus tool so that you can get to know the commands, or you can just go through the user guide and search for DFT if you want to know about the DFT scan insertion. So I'm just showing some list of commands where you can just insert scan cells. So I'm just doing help star DFT in your genus tools. So there will be some set of commands where you can just do the insertion. Again, it will depend on some of the inputs. So using this commands, you can just do the scan insertion of the cells. So if you're not knowing any commands, just do help star on it so that you can just go to man page of that particular command and you can know the description or the usage of that particular command. Okay, we can do directly physical synthesis without doing logic. As I told you, physical synthesis needs an extra input called as def or a floor plan def. Now that floor plan def is generated from logical synthesis netlist itself. So you should do logical synthesis first, then only come to physical synthesis. It's not like you directly can do physical synthesis. Yes, we will be replacing the normal flip-flops with scan flip-flops. Yes, that is what is DFT means. So it depends upon the commands. Again, there is another script to run the scan flow also. So that is usually not, I mean to say, it is not needed for a starting user. You can just go through the commands and there will be a user guide also to how to use the commands to run this DFT script. Okay, how the gate count reduces in physical synthesis. Okay, before answering that question, did you understand what is the physical file we are giving for physical synthesis? Anil, what is the extra physical input file we are giving for the physical synthesis? Did you understand what was that? Yes, the def file. Yeah. Now, I told you the def file contains the pin attributes, I mean the pin location, the memory location, wherever it has placed. So the floor plan def usually consists of the pin information where it is placed when it is taken to floor plan stage, and if there are any memory objects in my design, where are those memory objects placed and the area in which this pin placement have been done. Now, in the logical synthesis, you don't have any such kind of information. That means you don't have any pin location, you don't have any memory location, and you don't have any area that is needed for the conversion of gate level netlist. So in the logical synthesis stage, the tool will not be assuming the area constraint. It will just randomize and it will just convert the gates according to the random number of area. Now, when you do physical implementation, you are providing this information, that is the physical information of the pins where it is placed and the location of the memories where it is placed and the vacant area. Now you are telling the tool only this area is left for me, optimize the gate count according to this area. That is how area optimization is happening. Is it clear? Okay. Yeah. Any queries you can ask, or shall we close the session? Yes, def file will be coming from the physical design tool and left file will be coming from the foundry.
I think there is looks to be looking at the questions. There is confusion about def file. See, physical synthesis, in other words, it is also called physical design. Okay, so don't get more confused now, because of the fact that the inputs what we give for physical synthesis are two important files, two important inputs. One is left file, right, and other is def file. Okay, so Shravanti clearly explained where left file comes from. Left file is for, it is coming from
Sir, it is not audible actually.
macro. So macro, what is macro also she explained actually. Basically, now there are certain elements you are not having, is it?
Not properly audible,
Is it better
sir.
now?
Your voice is not audible properly. Your voice is breaking.
Okay, now is it okay?
Yeah, go ahead.
Now
Now it is okay.
Okay, so what I was telling is there are two important inputs for the physical synthesis, unlike logical synthesis. Logical synthesis, we give one primary major input, that is RTL, right? RTL. So then we are expecting the netlist from the RTL. Other constraints will give design constraints as per the architecture specification, design constraints we will give, right? When you come to physical synthesis, we are giving two additional important inputs. Those are left and def file. Left file, library extension format, this is basically given either by the foundry or some other design house, where there this geometry, all this information for a particular block which is hardened. Okay, so Shravanti explained about the hard IP, right? Hard IP means, see, especially memories. Memories, some companies like Micron, Intel, those kind of companies are very good memory designers. So they will directly give, see, if you have a chip here, in the chip, the whole, now I am designing a chip. This is my logic. My logic means I am right from RTL I am designing. So this particular block, which is coming from some other company or some other, even it could be directly coming from the foundry. Now, when I am considering the physical design and even the synthesis, I don't have access inside this. I don't have access inside this particular block. This is called hard IP. And for this hard IP, in order to see what is the power, what is the information here, I will try to get that is available to me in the form of left file. That is one form. That is for hard IPs. Okay, so that is left file. But for power and other considerations, I use in this physical synthesis to estimate. Similarly, now when I do the physical design, taking this netlist for this also, at the output, as an output of your physical design process, I get def file for this. This is my output of physical design process for the def file. Now, why I use in this physical synthesis? In order to get more realistic numbers here, okay, more realistic numbers in terms of power, in terms of other things what you are considering for the power, timing, right? I use def file for more realistic analysis of power, my timing, my area, right? For those things. So basically, def is output of physical design. Left is also, they have done the design process for this memory, but I am using here for my analysis in the physical synthesis process. Okay, so that's where Innovus tool, right? Some of you are mentioned. Definitely, in order to generate this def file for this particular block, I use Innovus tool. Hope this clears, the your questions about def. Is it clear?
Yeah, def and left files are input to the physical design type, not output, right?
Okay, def
Hello?
yeah, def file is an output of physical design tool. Left
Physical
file,
design.
library exchange format file is an input file from the foundry. Def is an output of physical design, but we are using here as an input file for doing synthesis.
Mhm.
Yeah.
Yeah, that is what
Yeah.
Okay.
in our practice also we use it as input, right?
Yes, we
For
are using it.
synthesis.
But what from where we are getting that input
But
is as an output from PD tool.
uh-huh.
So I think hope that is clear. So now we will end the session.
Okay.
Okay. Thanks a lot. I think
Okay.
some of you are mentioning that it is going over beyond 8 o'clock and all that.